Hello everyone, this is the environmental science content video for the beginning of Unit 4. We're going to start talking about populations. First we're going to go over how we describe populations a little bit more in depth. We're going to talk about how populations interact with one another, and then we're going to take a step back and look a little bit closer at how we talk about the human population because, we're humans. All right, so let's go ahead and get started with section 1, and we're going to talk about how population sizes are naturally regulated while we talk about how they're described, because those two kind of go hand in hand. So when we're talking about populations, we go by pretty much these three different properties. First, we're going to talk about that population's density, so how close the individuals live with one another. We're going to talk about the population's dispersion. So if they live in groups or if they are uniformly spread or they are at least look like they are randomly allotted to the area that they live in. So the three examples of that are below in these boxes. Uniform dispersion, you can see that there is a similar spacing between each dot. Random dispersion, there are some that are very wide spread out. There are some that are really close together. And then clumped dispersion, we've got these small areas where there are a lot, and then the rest of the area, there's nothing. We'll also look at growth rate for the population. And when we're looking at growth rate, it gets a little complicated, mainly because the math. But we're not going to spend that much time on the math. This is high school. Right, so the growth rate that we're going to talk about mainly is the change in population size, which equals the total amount of births minus the total amount of deaths. And we usually use this on a per year basis, though sometimes if we're looking at like a population of bacteria, that may be over a day or two or hours even. Right. The other value we're going to talk about is the reproductive potential, which is the maximum amount of offspring a single individual could have. And that relies on three different factors. We've got the number of offspring per cycle. You can think about this as like how many puppies or kittens are in a litter. Usually humans, that's one, maybe two. Very, very rarely does it get larger than that. But if you look at, say, frogs, you're in the hundreds. How often reproduction occurs. So if a baby is born on average once a month, once a year, once every 3 or 4 years, once a decade even for some animals like tortoises. And then when reproduction starts actually has the largest impact on the reproductive potential of a individual. Because if a person, let's say, starts giving birth to a baby once every year in their late teens versus in their mid to late 20s or mid to late 30s, that's making a larger impact because those kids also are going to be having that same amount of births per their lifetime. So it's going to have what's called exponential growth. Right? And exponential growth uses this formula here that is below my face. And it is capital P, which means the total population after time, T. So we'll talk about what T is in a second. P sub naught, or P sub 0, where that little subscript 0 is following it, is the starting population. So that's how much you have at the very beginning of your time period. The rate of growth here is this thing that we just talked about, the births minus deaths. So how many new individuals are entering the population minus how many are dying and leaving the population. If we're talking about a human population, we also may figure into the immigration and immigration, the I versus the E. You learned that in the vocab, or you are learning that in the vocab, where people are coming into the population or leaving the population. Right? That may also get factored in there, but disregarding people migrating, we have the percent rate of growth. And then T is the time in hours or years. Right? So this just depends on the scale and how long you're given. And then we have a constant called Euler's number, which on your calculator you'll see is a little e. And it's 2.7182, yada, 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 yada. It keeps going. It is a constant, and it's used for a lot of different calculations. This one, it is the base. So walking through this example, we've got the starting population multiplied by E, Euler's number, raised to, so we'd use that exponent, the little caret on the calculator, the percent rate of growth. So this needs to be a decimal too. So if it was 90%, it'd be 0.9. That would be really big, by the way. And then time in hours or years. Make sure that if your value here is expected to be in years, this needs to be in years too. If this is in hours, that's in hours. We're not going to do a whole lot with this. I more want you to be like, oh yeah, I've seen that kind of thing before. This is more what we're talking about. But with this exponent here, it means that instead of seeing a short linear growth, we're going to see an exponential growth. You guys have learned about exponents in math. You've done some exponential graphs even. All right, so continuing to talk about a population in an area, we can look at the carrying capacity of that area. You guys have already talked about carrying capacity. Everybody should know that carrying capacity is how much population a certain amount of land can support. If you go over that, the land could be damaged itself. The habitat may not be able to produce as much food for the consumers. Right? And there just may be resource limits. There may not be enough water. There may not be enough food in the habitat to support it. We also have something called competition, and we're going to get more into competition in the next section, so I'm not going to go very much in depth here, but it's when one individual or population uses the same actual resource as another one, so they kind of butt heads and will fight over it. Maybe not actually fighting, they may just suffer the consequences of there not being enough. So if we look at a graph of an example deer population, it might look something like this graph, where we have an exponential growth of deer, and they're more and more deer, more and more deer, and more and more deer, until they hit this point where something happens, and a lot of them start to die off, as in more are dying than are being born, so the birth rate decreases, so we get this negative slope. All right, and the deer population goes down. Usually this is because there's just not enough resources to support it, or maybe there are a large amount of wolves that move into the habitat because there's so many deer. But because of this, that large amount of deer, we see that the carrying capacity of the habitat is damaged. And it is damage that is repairable over time, but it takes a long time. Right? So all of this carrying capacity goes down and their population goes down. Eventually it starts to go back up, and it starts to equalize at the carrying capacity. It reaches a point of equilibrium. That's a word we've used before. All right, so here's another one. Here's plant and animal dynamics during population growth. So this is the same concept, right? But we're looking at the population of deer and the population of the plants that the deer eat. So very similar here, right? So as the deer have exponential growth, they're eating more and more plants. So their population of plants goes down because they aren't able to reproduce as much. Until eventually, the plants can outproduce the deer that are consuming them. And then they start to mirror each other. When one goes higher, the other one starts to go back lower. When that goes lower, this starts to get back higher again. Right? So they are competing, but they're competing for the same actual resource here. One is being a predator of the other, or a consumer in this case. All right, one thing I want to throw out here at the beginning of this unit, because we are going to talk about human population here, is this map. And this map I really like. I know it's a couple of years old at the time of the recording, and these numbers are much bigger than they were, but it gives you an idea of the relative populations for the different countries. So we've got each little square here, and if you zoom in really closely, you can see like the tip of Florida is a single square. Up here, there's another single square. So each one of those is 500,000 people. All right. So you can see the difference in population of China versus India or Spain or Portugal, the Republic of Ireland and England, the US versus Canada. Now, we're all familiar with a regular global map, right? That looks very similar to this, but this one has those nation sizes. The continents themselves have been misshapen because of this unequal dispersion of human population. Right? Look at Russia. Russia usually extends all the way over to this side of China, but it doesn't because there's a lot of places where people aren't living. The same with China. China is usually larger than this. It stretches to like here. Right? Just food for thought. Okay, we'll revisit this later in the unit. But for now, remember how our population size is naturally regulated. They are regulated by their food sources, and if they get too large of a population that can actually damage their habitat, they are also limited by predators that will feed on them.